So in this video we're going to talk about internal material balances on a distillation column for a special circumstance, one in which we have some kind of side stream that we're going to pull off with a different composition than our product in our distillate and our bottoms. So let's create an example problem and we'll work through this. So here we have a problem where we have methanol and water being fed into a distillation column. You can read the details of the problem statement and go along as we move through the problem. But the main point here is that we are looking to figure out where the optimal stage is to pull off a side stream with a certain composition that's different from the distillate and the bottoms. So first things first, we should draw a diagram and label it appropriately. So here's our information for our feed, 500 kilimoles an hour. It's a 50-50 mixture, and 50% of it enters as a vapor and 50% of it enters as a liquid. Now I'll go ahead and write our duties for our condenser and our reboiler, but it's not part necessarily for this problem, but it's good to label it. We also have our distillate, which has 0.95, and our bottoms at 0.05. And although it's not told to you, you need to figure out what component that's talking about. Since we're talking about methanol and water, methanol being the more volatile component, both these compositions are for methanol. And we're operating at 1 atmosphere, and we have a side stream that is a composition 0.75. The last thing we know is that the reflux is 2, but there's some other things that we could draw in here that will help us solve our problem. First, we know this is vapor going into our condenser, so we'll label that as V. We also now know that we have liquid going back into our column since we were operating a total condenser, and that's what's going to happen. We have some liquid entering our boiler. It's going to be at a different flow rate since we have a feed and side stream that will alter our internal material balances. We also have a vapor, which will designate V bar, that's leaving our boiler and entering the column. So we know that we have V bar and L bar at the bottom of our column. Somewhere at the feed, we're going to have a change in those, in which we'll say we have V now. And since our side stream is only taking off liquid, we will not be changing the flow rate of the vapor, given that we make the appropriate assumptions. However, this L that comes in does change, and so we'll label that L prime. And then L prime will change to L bar since we have a feed that's contributing to that flow rate. So after drawing the picture, it's good to write down what we're looking for. We are looking for a feed stage. We're also looking for where our side stream stage will be, and we're looking for the total number of stages. It's good to make our assumptions up front, and in this case for our distillation column, it's a good assumption to make the constant molar overflow assumption, also known as CMO. So how do we start this? Since we're using vapor-liquid equilibrium information to separate two components, it's probably important that we get that data first. So we would have to look up vapor-liquid equilibrium data for methanol and water so that we can plot all of this on our McCabe-Thiele diagram. One place to do this would be Perry's Chemical Engineering Handbook, and that's where we got this data for methanol and water. So I will show you that. So we've built our XY diagram with our 45-degree line, and now we could start trying to determine our operating lines for the column. So a great place to start is in our rectifying section, and we're going to not look at the side stream right now. So we'll just take a look at this area that I've highlighted in a box and write a material balance for what's coming in and out of that region. So we'll call this area right here that involves our reflux and above our side stream pull off section 1. So as it's drawn, the only thing we have coming out is D. We also have V entering and L leaving. And we're saying that L naught is going to be the same thing as L in this case based on our assumptions for CMO. So we write two material balances, one where V is equal to L plus D, that's our overall balance. Then we could write one for methanol, do a component balance. We combine these and solve for Y so that we could get a relationship between Y and X and plot that on our YX diagram. So as it's shown, this is our operating line for our rectifying section above the side stream pull off. Now, although we haven't done material balances on the entire column itself to try to get some of these values yet, one thing we can do is relate our LD and V to our reflux ratio, which we are given. So now that we've reorganized this into terms of our reflux ratio, and that's something that we're given, we have a nice y equals mx plus b type equation, and we could plug in our reflux ratio to get a line that has a slope of 2/3 plus an intercept of around 0.3. So we could plot this on our xy diagram. So we start at our x equals y intercept of 0.95, and we go to a y-intercept around 0.32, and that slope of that line should be 2/3, and that's something you could check. So remember, one of the solutions to this line is x equals y equals the distillate composition, xd. So this is our top rectifying line. So one down, 3 more to go. I'm going to go ahead and write our feed line equation, which is explained in other screencasts for distillation. And this is given in terms of a Q value and our composition in the feed. So what is our Q value here? Q is defined as the amount of the feed that crosses the feed plate. And so that has to be in the liquid state. So if we designate L bar as what goes down and L as what's coming in, then that change, or our feed, is going to be a ratio, which we'll say is Q. So we could rewrite this in terms of the fraction that's vaporized. And we know that this value is 0.5 from the problem statement. So our Q line, or feed line operating, is just going to be y equals minus x plus 1. So we can go ahead and plot this on our yx diagram, which will look like the following, where we start at x equals y equals the composition of our feed, 0.5, and we have a slope of -1 up to an intercept of 1. So in the past, if we didn't have the side stream, we would just take that intercept and draw down to our composition in our bottoms to get our stripping line. But we have a side stream, so that intersection here actually doesn't mean anything because we have an operating line that goes in between that feed and our top rectifying section. So we need to figure that out. So we need another section that includes our side stream here to our feed. So this is still part of our rectifying section, but we'll call it section 2. And I'll blow up this balance so you can see what it's going to look like. So this is the region of interest that we're doing a material balance around, which includes our side stream. So we know that based on the vapor flow rate going into our condenser, that above our side stream we'll have the same vapor flow rate using our assumptions and the same liquid flow rate that's coming in. However, now with the side stream being pulled off, we have a different liquid flow rate than before, and we'll designate that with a prime sign. Thing is, the side stream is pulling off a liquid, so the stream going up as a vapor can stay as a vapor. So now we know we have some terminology that we've designated for the system, and we could write the same material balances that we did before. So our overall balance is going to look like this following, and then we'll do a component balance, which I've simplified already, and drop some of the tray nomenclature since we're assuming CMO. And just like before, we could solve for y. So this becomes our operating equation for that middle section designated as 2 in the diagram. Now obviously the trick to plotting this would be to know some information about those variables, and we know xd and xs, but we don't really know about the flow rates. So a good place to go from here would be to do what material balances that we can to solve for our flow rates. So an overall balance on our distillation column gives us the following, where the feed has to be equal to the distillate, bottoms, and side stream flow rates. The component balance for our methanol, or any component for that matter, will give us the following. And as you can see, we have a lot of unknowns in only 2 equations. But we were told that our side stream was 100 kilomoles an hour, and our feed was 500 kilomoles an hour. We were also told compositions. So plugging in these values into our material balance shows us that we have 2 equations and 2 unknowns, and we could solve for D and B. After solving, I get a distillate flow rate of 172 kilomoles an hour and a bottoms flow rate of 227.8 kilomoles per hour. So that's great. That gives us ideas on the flow rates leaving and entering our system. However, what we're really interested in is those operating lines, and as you saw before, we have to figure out something about L, V bar, L bar, L prime, so forth. So we need some relationships for those. First place to start is our reflux ratio, which we know is the amount that's sent back into the column over our distillate. As you can see, that's going to give us our liquid flow rate into the column. And that should give us 344 kilomoles an hour. Next thing is we could figure out what L prime is. And the reason we could do that is if we think back to this drawing, we have L coming down, we have a side stream being pulled off, and then we have L prime. So L minus L prime is going to be S. So this should be lower since we're pulling something out. We have 244.4 kilomoles an hour of our L prime flowing down. The last thing we need for our operating line is our vapor flow rate V, and we know that that is equal to L prime plus our distillate plus S from one of our overall balances on that section. Plugging those values in, we could get the vapor flow rate to be 516.6. So if we go back to our section of interest for our operating line, we could plug in values for L prime over V as well as our other flow rates and get an equation for this section. So we have a slope, y-intercept. We know it's going to intersect with our rectifying line. Since it's a saturated liquid and it's at 0.75, we could draw that. So the side stream is kind of like an opposite of a feed. So we would start at x equals y, 0.75, draw a straight line up for our saturated liquid. And at this point, this intersection matters. The rest of the line does not. And now we have an operating line for our middle section between our feed line and that side stream. We know the slope is 0.47 and our y-intercept is 0.46. Just use the y-intercept. That becomes our middle operating line. And here again, all we care about is that intersection and not necessarily the rest of the line. Same thing with our feed. Then the last line to draw would be our stripping line, and we could do the same thing as we do for other cases. Go from that intercept to our composition on the x equals y line of 0.05. And we've drawn all of our operating lines for this column. Now the real question is, where are we pulling the side stream and how many stages are there? So the first thing that we would do is draw a stage that precisely ends at our side stream. Because we're pulling off a liquid, it has to have that composition, so it has to be at that stage. Then we would just continue filling in stages throughout the diagram to count how many stages we have and where our side stream stage enters. So remember, when we cross over those intersection points, we drop down to the other line. Since I've cut those lines short, it's easier to see that. So we start counting them off. Since we have a total condenser, we start stage 1, stage 2, stage 3, and that would be our stage for our side stream. Then we have stage 4, stage 5, stage 6. So our feed stage is stage 6 because the intersection occurs between stages 5 and 6. We have 7, and then we would have our partial reboiler. So we have 7 stages plus a partial reboiler. We have a side stream being pulled off at stage 3 and our feed being fed at stage 6.